Welcome, everyone. Welcome to Strait Science. Strait Science is an evening seminar series put on by the University of Alaska Fairbanks Northwest Campus in Nome, and also by University of Alaska Fairbanks Alaska Sea Grant, also in Nome. And tonight's Strait Science is going to be away from the ocean tonight, and we are going north of Nome. And this is a talk that's going to be on the geology. I know that the Graphite One Project has got a lot of people that are pro and against, but on this talk, we're sticking to the science of the minerals that are north of Nome. And tonight's, I should say, Northwest Campus and Alaska Sea Grant. We are public servants of the Bering Strait region. We serve all peoples of the region, which is the homeland and waters of the Inupiaq, St. Lawrence Island Yupik, and Central Yupik peoples. Okay, so now our speaker tonight is Kirsten Fristad. She is taking time this evening out of her busy day to give us an opportunity to learn more about graphite and the geology of the Kiglualk Mountains. So that's something I'm really unfamiliar with, and we're going to hear it from the top-notch. Kirsten is the chief geologist for the Graphite One Project, and she's in Anchorage tonight, and she has asked that our questions can be as we go. So raise a hand or throw something in the chat box. I'll be monitoring the chat. And with that, Kirsten, we're so glad you're here to give us some opportunity to learn more about the actual geology of the region and what is graphite and what's it mean and actually some of, perhaps if you can, some of the other minerals and what that may mean. With that, take it away, and we're all ears.
Thank you. Well, thanks for having me. It's a pleasure to be here. And as you said, my name is Kirsten Fristad. I'm the chief geologist for Graphite One. I've been with the company for about 2 years. So I know for those of you that's been in the region, it's a project that extends back at least to 2012 and definitely has more history before that we'll cover a little bit. But what I wanted to do tonight is really give a general audience talk on the geology of Graphite Creek. So for some of you, this might be more technical than you prefer, and for some it might be less technical than you prefer, and we can kind of take it either direction as needed. But my goal really is to help you understand what graphite is, why some folks are interested in it, how we go up, like why it exists where it is, why we're even looking in this particular place for graphite, and how we go about the exploration process when we do mineral exploration. And so it's really meant to kind of just be a informative, fact-based presentation. So with that, we'll get started. I also want to acknowledge that there's many people that have worked on these mountains and on this deposit before in many different fields of science, but in geology in particular, George Case and Sue Carl that are at the USGS in Anchorage has spent a lot of time studying these rocks, writing papers about these rocks. There are a number of Canadian and Alaskan geologists over the last couple decades that have spent time here and have all really contributed to our understanding. And so what I'm showing you today is really a compilation of a lot of different work that a lot of different people have done and kind of a layman's understanding of where we're at today and our current understanding of these mountain systems and how they got to be where they are. Figure out how to advance slides here. Okay, so there's a couple, I want to kind of guide this talk with some questions. And so the first question is, what do we use graphite for? What is graphite? Like what is this word and what is this stuff that we keep hearing about? Then we go through how it forms, why there is graphite in the Kiglualk Mountains, and then how we know where the graphite is located at Graphite Creek in particular. So here's a little overview. A photograph taken in the summer of 2024, which was my first summer field season up at Graphite Creek when we had, that was sort of our last big fieldwork summer before we wrote our feasibility study. And here's some examples of the core that we got out that year. So to start with, what do we use graphite for? Humans have used it for many different things for probably thousands or more years. Some of probably the oldest uses of it were as pigment. I actually found a guy who does tattoo research and found this really beautiful photo of a Yupik woman they use graphite in the pigment for tattoos. I thought that was a really neat piece of history. Certainly you probably have heard of it in pencils. That is a place that we on a day-to-day basis maybe interact with graphite. But when we think about making other objects and other materials in our world, we use various materials to make other materials. And graphite is one of these hidden sort of substances that is used a lot of different places in ways that you might not realize. So one is for crucibles. It has really neat thermal properties. It's used in the cores of nuclear reactors as a radiation shield. It's used as an industrial lubricant. It's really slippery. It's used for that. For a long time, one of the biggest volumetric uses was as electrodes in water heaters. But the big thing that has really brought graphite to the forefront and sort of put it on the critical minerals list is its use as an anode material in lithium-ion batteries. And these can be any kind of lithium-ion batteries. You think power tool, like cordless power tools, your phone. But those batteries are physically small. So it means just in terms of total mass, they have graphite in them, but not pounds and pounds of it. But the biggest sort of place that you put a lot of graphite would be in electric vehicle batteries. Electric vehicles have very heavy batteries, several hundred pounds, and almost half of that material is actually graphite. And so it's really the development of electric vehicles, municipal scale batteries, like sort of power grid scale batteries. That's where there's a lot of graphite going into those batteries to make the batteries work. And why we kind of maybe care about this in the US, particularly when you look at where graphite is currently mined from the ground. A lot of it is from China. There are many other deposits of graphite around the world of various sizes, Madagascar and Mozambique and Brazil being some of the larger producers. But ultimately, all that graphite ends up going mostly through China to get processed. And when we look at the graphite that we use here in the US, all of the graphite that has been processed and is ready to be put into some kind of industrial use, we have to import. We currently don't refine or sort of prepare any graphite here within the US. And so we have this 100% import reliance on it, which is one of the reasons that led our company to be interested in not just thinking about opening a graphite mine, but also producing processing facilities, which we're working on building in Ohio as a company, where you can get graphite from a number of different sources, but put it through the refining process and sort of finish it off so it's ready to go into the products like lithium-ion batteries that use it. So what is graphite? Basically, it is made of carbon. So if you recall high school chemistry, here's a picture of our periodic table. I've got carbon circled here. What else is made of carbon? We are largely made of carbon. All life as we know it is carbon-based. We're made of many other elements as well, but carbon is one of the main constituents that we're made out of. And so in that way, there is sort of a very neat connection between life and graphite. Carbon can form two main minerals in the earth, and I'm pretty sure you've probably heard of both. So the first is graphite, and the second are diamonds. And the main difference between graphite and diamonds is their molecular structure. And that molecular structure then leads to different properties. So I guess I should have asked, can you see my mouse? Is that a thing that is visible on the screen?
We can see your mouse, yep.
Okay, great. So these are atomic diagrams here. So on the left, we have the structure for diamond. The little circles represent carbon atoms, and the little sticks represent the bonds between those atoms. And here you can see that diamonds have a really three-dimensional bond structure. which gives them a property of being very hard, right? Diamonds are famous for being quite hard. And if you look at the graphite structure, we have our little carbon circles here. We have nice sticks bonding them together into hexagonal rings that make sheet structures. But then, so the bonding is quite strong along the sheets, but between sheets, we have a weaker set of bonds, and sort of represented here by the dotted lines. And these weaker bonds between the sheets of graphite give them different properties than the diamond. We have some little pictures here. This is actually one of the largest diamonds found in the world recently in Botswana, quite huge. And then here's a piece of graphite. Can look a little different. It's hard to photograph graphite well because it's so dark and shiny. And just as a little reminder, rocks, you think about the difference between rocks and minerals. Minerals are composed of atoms that sit in a geometric structure that is infinitely repeating in 3 dimensions. And rocks are composed of one or more minerals. So often you'll hear of many different minerals that sit inside a rock, and we'll talk a little bit about that as we go forward here. Let's get rid of these. Okay. So the properties of graphite. Ultimately, the properties of graphite really come down to its molecular structure, which is why I think it's interesting to point out. There's 2 main properties that are the reason it's really interesting as a material for humans. One, it's an excellent conductor. And what that really means is the electrons, so along a sheet, because you have this tight bonding between carbon atoms, the electrons can flow very freely along these sheets, and they can act very much like an electric wire would, and send electric signals very easily along that structure. And the other main property they have is it's really slippery. Remember, it's often used as a lubricant, and the reason for that is between these sheets, the bonding is weak, and you can get a lot of slip between sheets, and that makes it very slippery, which makes it a good lubricant. It also makes it hard to do things with graphite like crush it, because it's so slippery, it just starts sliding on itself, and it's hard actually to crush the way you would crush other kinds of rocks. And this is an example of what a lithium-ion battery looks like. So you have a cathode and an anode and a battery, and you have like a charge-carrying ion. In this case, would be lithium, would be little red dots that goes back and forth. That's what makes your battery work. But in the lithium-ion batteries, right, this anode material is the graphite. So you can see the graphite structure in here. So how does graphite form? You can actually make graphite artificially or synthetically, or you can make it naturally. And what I'm going to focus on in this talk is the natural graphite, because that's what the earth does. It makes natural graphite. It's a pretty similar process though, actually, if you're going to make artificial graphite. So here is one of the more technical slides. This is a pressure temperature diagram. And if you look at the 2 axes, we have temperature here. It's in Kelvin. So don't worry too much about the actual numbers. The general idea is that as you go to the right, temperature is increasing. And it's increasing significantly, way beyond. So like if we're on the surface of the earth, we're basically at the origin of this plot right here. And as we go up the y-axis, we have pressure. This is in gigapascals. And also the pressure gets quite high on this scale. So for those of you that maybe know where diamonds form, and here you can see it's in this pressure temperature space that diamonds form. So basically across a range of temperatures, but only at really high pressures, you get diamonds forming. And if you know where they form deep in the earth. So basically this zone here, all up here, is where you're sort of deep into the earth. Here is basically its surface. Graphite forms. So if you take a bunch of carbon and move it into this space on the diagram, so this sort of range of temperatures and this range of pressures, you form graphite. So basically graphite forms when you have higher temperature and a low to medium amount of pressure. And if you took that graphite and moved it deeper into the earth, increased the pressure, you would turn it into a diamond. And these pressure temperature diagrams are really useful in geology when we think about metamorphic phase transitions, how minerals change from one mineral to another as they move to different environmental conditions. So different pressures or different temperatures, they deepen the earth. But this is sort of one handy way to think about graphite and the space that graphite might form in. So basically, does graphite form at the surface only if, so here, if we have at the surface, we have low pressure, only forms if there's high temperature. And so if we want to make synthetic graphite, for example, what we can do is we take carbon, we can put it in a furnace, we can heat it up really hot, we can make graphite. If we wanted to take that graphite and turn it into a diamond, we would need to add pressure to do that. And it is possible to make synthetic diamonds as well, right? Often you find them on, say, drill bits or other often usually industrial uses like that. So this is kind of the relationship between graphite and diamonds in PT space, as we would say. Up here. So where does graphite form in, if we think about kind of tectonics and the Earth as this moving system of plates? Maybe some of you have seen this either in a geology class or, I don't know, a Nova special at some point. But this is a cross-section view of a classic subduction zone. So here we have continental crust on the right. We have oceanic crust here on the left. There's a lot going on in this diagram, but the main thing I want to highlight is that at subduction zones, you have oceanic crust that starts getting pushed underneath continental crust and gets deeper and deeper. And so if we think about how we can take a sediment, turn it into a rock, and then watch the minerals in that rock change from, say, graphite to diamonds, we can think about what happens here in this diagram. So if we think about the ocean is where we have a lot of organisms living and dying and eating each other and recycling carbon. And there's a lot, and I think probably a lot of other talks get into all the things that happen in the water column here. But as geologists, we kind of think about, okay, of all the things that are happening in the water column, what actually makes it down to the sediment at the bottom? And there's generally always a small amount of this organic material. So the creatures that are living and dying, often algae, small creatures, there's a lot of volume of small creatures that make it all the way down to the sediment and get buried in that sediment with other clay particles, silt particles, sand grains, things coming down to this deep ocean floor. As those layers build up, you had lithification. So that organic, we call it organic carbon, the carbon that was part of a living creature gets locked in there, buried in there, and becomes part of the sedimentary rock that's forming on the ocean floor. Well, if we take that carbon-bearing rock on the ocean floor and start subducting it. So this is a small little picture, but a picture of what a lot of organic carbon molecular structure can look like in these sedimentary rocks. It's like a tangle of little carbon atoms with bonds going every which way. It's not well organized. It's not well structured. But as you bury it and the rocks start subducting and get deeper, and the temperature goes up and the pressure goes up as you get inside the earth, you can form graphite. And for example, if you keep taking that carbon deeper and deeper, you can form diamonds. So one thing to think about is, where do we have, like in today's world, where do we have this kind of a tectonic margin? We have a really big one in Alaska, right along the Aleutians. So the Pacific plate is pushing north and getting subducted underneath the Aleutians. And as it goes down, the crust starts melting and coming up and making volcanoes, just like you have in this diagram here. There's isn't really continental crust quite behind it, but you get the islands of volcanoes is basically what we have here with the Aleutians, right? That's similar to this diagram here. Well, in Earth's past, there have been many of these subduction zones that have formed and at some point stop moving and maybe switch direction. push up and move rocks up. There's a lot of different dynamics that can happen here with these crust or with the crust, and that's one of the things we got to think about when we look at the rocks on the surface today and think about what kind of tectonic forces they might have experienced in their past. What's going on? Okay. So I'm going to attempt to play this video. We'll see how this goes, this link. This is a really neat little sandbox experiment that you could totally do at home if you wanted. It's done at the University of Otago in New Zealand, and it's a geology lab class. But I think it gives a good visual to help build some intuition around how layers like rock layers can deform when you have compression and we have two sections of crust running into each other, and how uplift can happen. So ultimately, if we see graphite on the surface, we probably had a setting where we had subduction, and so that rock went down deep to form the graphite. And if it's back up on the surface, that means somehow that rock went from down deep back up high to the surface, often forming a mountain that then can get eroded, and we can see the graphite. So this video kind of helps, I think, visualize how some of these down deep layers can go up high. And this is just a little intro here. I'm going to pause it briefly. You can see this is all sand, but it's amazing. The rock actually behaves very similarly. It just happens over much, much slower and much longer time scales. So if you bend solid rock slowly enough, it will deform in a very similar visual pattern to the way this sand is deforming. So there's just different layers. They each have different colors. And this wall will be coming in, and you can just watch and see what happens. Keep an eye on the deep layers and see kind of where they end up as the compression moves forward. And I think they're measuring various things here for class, but I can even zoom up a little bit. But basically, as we move forward, some of these layers that originally were quite deep are getting higher and higher. And you can imagine this is essentially a mountain building event, right? So you can see the surface here is moving up high, turning into a mountain. When you have rain, snow falling on a mountain, what happens? You start getting glaciers that cut and incise valleys. You start getting drainage networks, creeks, gullies that cut into that rock. And so you start being able to erode some of these top layers and exposing, either in creeks or if you get the entire surface to erode, some of these deeper layers on surface. And ultimately, that is a lot of what we're seeing in the Kiglualk today. We got the gist of this. And go to the next slide here. Okay. So to move to the Kiglualk Mountains, so why is there graphite in the Kiglualk Mountains? So I tried to give a little background here, sort of geology 101 background on how we can make graphite, the tectonic settings required to make graphite. Let's look at the case example that we have here on the Seward Peninsula. So to get oriented, we have a map of Alaska, right? We have the Seward Peninsula. If we zoom into that, oops, my little box didn't get relocated. Here we have Nome. We have the Bering Sea over here. We have Teller and Breivik Mission, the Emmerich Basin, and Council, and the roads here drawn in for reference. So the little star represents the Graphite Creek deposit, as it's known. Here, there's just the orange boxes are the claim blocks around the Graphite Creek deposit. But what we see here is you can see in the relief map, these are the Kiglualk Mountains. And the Bendelabens continue up this way and go behind this map. But what we're really going to be then talking about here is this set of mountains. So anytime we see mountains, we know somehow they've been pushed up through some kind of tectonic action, one way or the other. There's a couple different ways to push mountains up, but one is what we just saw in that last video. So that's something to always think about. But really then once we know there's mountains and it's material that's been pushed up by Earth's tectonics, it's interesting to take a closer look at what kind of rocks are there. And are these rocks that that kind of fit the formation mechanism as we understand it for graphite? So this map is a fairly busy geologic map that's zoomed out. And so I'm going to try to highlight some of the key points here. You can see here the Norton Basin as it's marked here on the map. Nome is right here. This would be the Bering Sea. So this is the Seward Peninsula. This is the Brooks Range coming across. So here's kind of the Alaskan western coast. And then this side over here is Russia. And the geology between Russia across the Bering Strait is quite similar and ultimately geologically connected to the geology that comes into the Seward Peninsula. And if we just sort of take this really stepped back view and look at some of the labels on this map, this region of the world has, in this the dark portions of the map are rocks that can be described as an oceanic assemblage. So sounds like a marine system. We have these rocks here that represented by the what look like little bricks are the standard geologic notation for limestone or calcareous rocks. And we see there's a lot of calcareous rocks here and then right here as well, north of the Kiglualk on the Seward Peninsula. The place that we typically form a lot of limestone would be a shallow marine area. So the shallow ocean is where you form those. And then this rather slightly gray, light gray tone here, it's called intermediate and low-grade metamorphic rocks. Okay, so big picture, we have ocean rocks, we have shallow ocean rocks, we have then intermediate, low to intermediate grade metamorphic rocks. And then in the little dark zone, we have what are called gneiss domes. So we'll get into that a little bit, but big picture, we have these ocean rocks and then some metamorphism happening. And then we'll figure out what gneiss domes are here in a minute, but that sounds like something else might be going on. So big picture, if we're thinking about tectonic settings that can form graphite, we have these marine sediments like we talked about. There's going to be a lot of potential in all these ocean floor sediments to have carbon buried in them. And if we have metamorphic rocks, well, there's a good chance that we have added heat and pressure and some kind of transformational change could have happened to that carbon. So now we'll take a closer look at the Seward Peninsula. So we're zoomed in a little bit. So here's Nome. Teller and Breivik are right here. This would be the Emmerich Basin. Here we have the Kiglualk Mountains here in brown. And if we look at sort of this scale of the Seward Peninsula, there's sort of three main color groupings. And this is work that was done by a map that was made by the USGS. Sort of, there's two different generations of information in here, but been done in the last 20 years. And so in the purple colors, we have what is called the York terrain. And if we look and see what kind of rocks those are, it says carbonate rocks, carbonaceous, calcareous rocks. So this is some of that limestone that we saw on the last map, or strictly speaking, it's had a little bit of change happen to it. So it's been metamorphosed. So we don't strictly speaking call it limestone, but it still would form in that shallow marine environment. In the green here, the green and the light blues, we have the Nome complex. So this is politic schist, carbonaceous, calcareous. These are some of the words we're seeing in these units here. These are also politic is basically a word for ocean floor mudstone that's been metamorphosed. That's the schist. And so we have this ocean floor rocks here. And then in the brown, we have either we can think of it as the Kiglualk metamorphic complex, or it's high-grade metamorphic rocks. And so we have this stripe of high-grade metamorphic rocks inside this larger zone of ocean floor sediments. So we're going to zoom in a little bit more. So now we're zoomed into that brown patch. So this is really just the Kiglualk Mountains. And once again, we can sort of look at the colors a little bit more. It's the same color scheme as before. So the browns are these medium to high grade metamorphic rocks. And this map has a little more information on what we call metamorphic isograds. So when you pick up a rock, one of the best things to do is start looking and identifying the minerals that you see in that rock. Every rock has a handful of different minerals. As we've been talking about, the minerals change their structure as their pressure temperature environment changes. And this is a really handy tool in metamorphic geology because certain minerals form under certain pressure temperature conditions. And so we use these minerals, we call them index minerals. And these index minerals can tell us what either degree of metamorphism we've had, which you can see in this chart here. You can think of it as low, intermediate, or high grade metamorphism. You can also correlate these to pressures and temperatures. And so you can think about what kind of tectonic environment would have had to exist for these various mineral assemblages to form. So when we look at this map, there's these little pink stripes, and these are what are called metamorphic isograds. There's 1, 2, 3, 4 of them on this map. And the way they work is that they're a line that delineates. So basically, if you walk from south to north, they're lines that delineate where you see certain minerals first appearing in the rocks. So the first line on the bottom, number 1, biotite is in. So biotite appears. Second line, you have starlite that appears. The third line, selimonite starts appearing. And then after the fourth line, you see selimonite and potassium feldspar. So I imagine by yourself, like just hearing these words, they're minerals, you may have heard of them, you may not have heard of them, doesn't immediately tell you anything until you start thinking about what space they represent as an index mineral. And so if we look at this chart, we're starting with a shale. So that's basically our ocean floor sediment. And as we go from low to intermediate to high grade, we can see these different minerals form. So if we suddenly have biotite appearing, that means we've at least entered sort of this mid-low grade to intermediate grade metamorphism. Starlite is here. So starlite indicates a higher degree of metamorphism. Selimonite, higher yet. And so the fact that we have the selimonite in these rocks as we move forward tells us that this was a pretty high grade metamorphic system. That means these rocks were subjected to high pressures and temperatures. What does that tell us about what other minerals are going to be affected in the rock? Well, that entire rock felt those same temperatures and pressures. So if there was any carbon in those rocks, they also would be transforming to whatever mineral is stable at those higher grade temperatures and pressures.
So this is Gay, Kirsten, and I'm just wondering, since you did say we could ask questions in the middle, could you explain when you're saying that metamorphosis and metamorphic, because that was part of the whole thing, like it was, and I'm not sure if everyone understands what that means. Is that okay?
Yeah. So you're asking, like, what does metamorphic mean, or metamorphism mean?
Yeah.
Yeah.
Thank you.
So if you think back to that pressure temperature diagram, well, I don't know where to start exactly, but basically, if you take a rock and you make it hotter and add pressure, the atomic structure of inside of the minerals inside of that rock will start shifting around.
So basically, the diamond analogy, the graphite,
Yeah.
you add more turning into, the diamond. That's what that's the process. Okay, so thank you very much.
Yes.
Transforming
so metamorphosis is the shift of one mineral using the same atoms into a different mineral structure.
Thank you so much.
Absolutely. Great question. Metamorphism is like a little trippy and hard to explain sometimes. Yeah. So, but ultimately what these index minerals then can do, because these minerals form under different conditions, when we see a particular mineral, it will tell us what conditions that rock must have experienced, right? And so basically, as we go north here in the Kiglualk, we have this increased and metamorphic grade, and we know that these rocks were subjected to higher pressures and temperatures. Okay. There's another feature in this map here, this pink color we haven't really talked about. And if we draw a cross section through the mountains, so one side will be up here and the other side will be down here. And now imagine we just take like a big cake slicer and just cut straight down along that black line. And then we look at it. So our A is on our left and our A prime is on our right. We're now looking at the cross section of these mountains, and basically all the brown stuff here is the same as the brown in this map. So it's these high grade metamorphic rocks. And what we see in cross section is we start to see their structure. And what that means is that we can see which direction the rocks are pointing or dipping, as we would say. So on the south side of the Kiglualk, they're dipping to the south. On the north side, they're dipping to the north. And in the middle, where we have this pink unit on the map, we have what's called an orthogneiss, or really sorry, my bad. The orthogneiss is in the middle here, but this is a granitic cap. So this is the gneiss dome that we were seeing on the very first map. So there, it turns out in the middle of the Kiglualk, and as you move through the Bendelebens, there's all these ocean sediments, but in the middle, there are these igneous bodies. So where we had molten rock that came up through the crust and pushed up. And how much of the structure, you see this sort of arching structure, some amount of the arching structure is probably from the crust pushing together and making a fold, and some amount of it is from this magma moving up in the crust and pushing up and doming the rocks. And because the rock is old and metamorphosed, we call it gneiss. And so we call these structures gneiss domes. And you see that along the crust of the Kiglualk and over into the Bendelebens. But that's where that term comes from. And that's really what we see here in the core of the Kiglualk. So this rock is very, very hard. If you think of like a magma that cools, like our granite countertop, it'd be like very similar to, say, a granite countertop kind of rock. The rocks on either side are these what were softer ocean floor sediments, but now are much harder and have metamorphic mineral assemblages from being metamorphosed.
Kirsten, yep, there's a question in the chat, and it says, are those dashed lines, I think in your current bottom,
like right here,
actual soil / rock on top, or have they been eroded already?
They've been eroded already. That's a great question. So in basically the solid line here is the modern day surface of the mountains, of the rocks. And what these dotted lines represent is that geologists think that this layer ultimately, once upon a time, connected back to this layer. And that ultimately, if there hadn't been any erosion, you would see all of these layers in one big sort of A-shaped fold, dipping from one side to another. And so that's how we represent that, just with the dotted line, to let people know we're pretty sure this layer is the same layer as this layer. And once upon a time, it would have been one big, probably flat layer cutting across before it got pushed up into this dome shape. Great. Okay. So this is kind of the general structure and the general, I guess, metamorphic setting for the Kiglualk Mountains. If we zoom in a little bit now and look at some of the rocks that we see there, we're actually just going to look at, these two brown units. There's a darker brown unit and a lighter brown unit. And these are the units that are along the north side of the Kiglualk, which is where the Graphite Creek deposit is. Graphite Creek is actually named after a creek, Graphite Creek, that cuts right through right about here. There's a number of other creeks along the Front Range here, and that's where a lot of the finer detailed work has been done, and George Case has written his paper on the rocks right here because that's where we had access with the exploration work we've done. So if we look at what these rocks actually look like, you get a feel for what some metamorphic rocks, how they can appear. There's two main units, and I'll say we have some observations here that are very geologic terms, but they might mean something to you, but they might not. If they don't mean anything, that's okay. It's not that critical. But the rocks themselves generally have a schistose to gneissic texture, which really means there's they have this sort of linear, we call it foliation. They look like stripes, like flattened stripes. And that's sort of the schistose texture. The gneissic texture is when you start getting larger stripes of color variation. So you can have this like white stripes and then dark stripes. And that's really what nice looks like, nice with a G. We also see dense layers of garnets. So here, these red sort of grape looking minerals are garnets. We see graphite around them. There's some of this dark silvery stuff. Like I said, graphite doesn't photograph very well because it's so dark and shiny. It's better in real life to see it. But it's interspersed here with the garnets. And then we have seliminite quartz layers. Remember, seliminite was one of our index minerals for these metamorphic rocks. And that's what grows here along with the quartz in these white zones. So the seliminite is we call it fibrous mineral. The texture looks a little bit like hairs or fibers. And the quartz tends to be more gray and somewhat transparent. And you can see that kind of on the sides here. Okay, so there's two main units that we have that I mentioned, that dark brown, the lighter brown. Here, they're in dark green and blue. So one of the units has a lot of garnets in it and has much thicker gneissic layering. So bigger zones of the white minerals and then bigger zones of the graphite and darker minerals. The other unit, we call it a quartz biotite schist or gneiss. This is an example of that. It's much more tightly packed. You don't get quite the same thick black and white stripes, but you do see that linear pattern to the texture. And when we look at these rocks, in a lot of ways, this is kind of what the ocean floor sediments looked like before significant metamorphism. When you start seeing this bigger zonation in the gneisses, where you have the white layers that are really separating out from the darker layers, that tends to indicate there's been partial melting. And this was one of the big, I think, steps forward that George Case really made, looking at these rocks, realizing that some of these rocks experienced such high temperatures that they started partially melting. And it turns out that when you try to melt a rock, the whole rock doesn't melt at the same time. Different minerals will melt first and different other minerals will melt later. So it's kind of like you put, a couple different kinds of chocolate chips and butter in a pan. Like that butter will start melting right away, but it takes a little longer for the chocolate chips to start melting. It's kind of like that. And it's so, in the case of a rock melting, the stuff that melts first often will migrate away, kind of get squeezed out of the rock and separate away from the stuff that doesn't melt immediately. And you can get this separation of phases. And that's one of the ways that you can get these larger, sort of darker and lighter stripes in the rocks. Another feature of it is that you'll concentrate certain minerals if they've been left behind, like the garnets, for example. And I know if there might be some questions about the rare earths, and these garnets are where we think we've observed we have rare earth elements housed in these garnets. And so ultimately we can talk about that a little bit more at the end, but But part of the reason for that is that they can pick those up during this partial melting event. And they kind of act like a little filter for some of those extra elements. As the garnets form, they're happy to take up some of those rare earths that might be otherwise mobilized or released from other minerals that have melted. So those are our two main rock units. When we look at the graphite itself, there are a number of different observations we can make. There's two main kinds of graphite, and one we refer to as disseminated flake graphite, and you might have heard that term before. Flake graphite, the Graphite Creek is often described as the largest flake graphite deposit, and flake really means that you have that, you think of that mineral structure for graphite, it makes like a flake shape, right? It's makes these sheets that can grow quite long, and so they're really platy. And so the flake refers to the fact that you have pretty large sheets that have grown in the rock. And that's really useful for certain applications and harder to find. Like a lot of times you'll find like smaller bits of graphite that don't grow into that full large flake size. And that's one of the reasons that sort of interest kind of got renewed in Graphite Creek, was because the abundance of the flake graphite. And then the other kind of graphite we have is this more massive or semi-massive lenses. We call them lenses or pods of graphite. And so the flake graphite you can kind of think of as like little bits of confetti sort of sprinkled throughout the rocks. In the lenses or pods of graphite, those have probably experienced the partial melting, and whatever graphite was sort of as confetti throughout the rocks has been consolidated into thicker horizons that therefore, when you measure them, are much higher grade. It could be 20% graphite over a 1 meter zone. But it's because all that graphite, instead of being sprinkled throughout in lower density, it's been sort of squished together into a small area and has created these really dense lenses of graphite. And you can see some examples of that here, where it's just pretty much solid graphite and like a big piece. And then there's another zone where there's like hardly any graphite, and you have that selemonite and quartz adjacent to it. Another thing that George Case did when he tried to understand how the graphite formed at Graphite Creek and where it might have come from, you can measure the carbon isotopes in any kind of carbon. So right, there's radiocarbon dating to figure out how old some pottery and ashes might be. Well, stable isotopes are a little bit different. They don't tell you the age of something, but they can tell you whether the carbon that's making something up is from an organism that was once alive, or whether it's what we call inorganic carbon. So say carbon that was just dissolved in the ocean, or as not part of anything that was living, or part of atmospheric, say atmospheric CO2 dissolves into the ocean. Then under certain conditions that can precipitate into limestone. That limestone, if there's no point along that path where that carbon was in a living creature and it's just going through this sort of abiotic pathway, it does not get fractionated, we say. So basically the carbon stays heavier. The carbon isotope value is closer to 0 for that carbon. When we look at this scale here, that at the top it starts at -10, so 0 is way up here. So limestone in the ocean typically has that 0 value. If it's not from living stuff, but just simply precipitated out of the water column. If the carbon somehow went through a living system, so it's like a buried algae, for example, then it has this isotope signature that's much lighter, which also it's sort of unusual notation, but have values closer to -20. And so we see here, George went through and measured the carbon isotope values. This is the ratio of carbon-12 to carbon-13 for a number of different styles of graphite that we see in the deposit. So it wasn't just one piece, but a number of pieces of graphite to get a good data assemblage. And you can see that they all are generally around this sort of -20 value. So this really does support the idea that these rocks, like when we look at the mineralogy and the metamorphic history of these rocks, it does in fact look like they were once ocean floor rocks. We look at the carbon values of the graphite, that also matches what would have been once buried organic carbon in those rocks. So the story is really hanging together with the data here, suggesting that the rocks here hosting Graphite Creek were originally ocean floor rocks that got metamorphosed, and that's now how we have graphite in these rocks. So he's got this lovely figure that has a lot going on. So I'll try to talk through in a basic way, but basically around 400 to 500 million years ago, that's when there was these oceans in the Seward Peninsula area was basically an ocean. We had this deposition, we had the burying of the carbon and burying of these sediments. That was certainly a long time ago. There's a number of probably metamorphic tectonic events that have happened since then. And we won't get into all the nitty gritty of that, but there's some hypotheses that there was partial subduction. And so that those rocks got buried to a certain degree, probably achieved or attained a certain amount of metamorphism through that. Ultimately, were brought back up to surface when tectonic margins changed, brought back up to surface. And then when that gneiss dome formed, that's also, I forgot to mention this, but as the gneiss dome forms and that magma comes up through the crust and makes that big arch, that's really hot, right? That magma coming up is extremely hot. So you have high temperature metamorphism happening in the sediments right around that to basically cook potentially anything there that wasn't already cooked. And so that's what George had seen in the temperature history of these rocks. And so that's what these lines represent here, is this in more recent days, only 100 million years ago, or just short of then, in the Cretaceous, there was this melting. And he thinks that one of the things that probably happened at that time as well is you had this partial melting of the rocks. So with all the heat coming into the system, you get this partial melting of the rocks, you get the concentration of the graphite into these big pods. And then since then, we've just had continuing uplift and exposure through erosion of these rocks to surface. And so when we go there today, we can see rocks that once upon a time were buried much deeper and were at much higher temperature than what they are now, certainly at surface, right? They're cold, cool, air temperature rocks at this point. But this is the sort of the genesis story, we think, of how the graphite came to exist at Graphite Creek. And one of the reasons that it is a place that's of interest to mine. And the reason I say that is because whenever humans think about trying to acquire a material, you want to think about, where is that material concentrated, right? There's ocean floor sediments that contain carbon a lot of places, even contain graphite a lot of places. But a lot of times that graphite is speckled through those rocks in really low concentrations, just as that little confetti, right? So it's still distributed in really low volumes, really low concentrations. The thing that's really unique and seems pretty special about Graphite Creek is this amount of partial melting that happened to really concentrate the otherwise confetti graphite into like these larger, thicker layers, where you could really have a concentrated mining effort. So that instead of digging up an entire mountain range to get all that graphite that's in confetti form, it's a small confined area where you have these thick pods and lenses, and you can just focus on that, because that's the only thing that really would make sense for a number of reasons. So here's a picture of a geologist out in the field looking at graphite at an outcrop in Graphite Creek. These white layers are the slimonite quartz I mentioned. The darker layers are graphite, and this is kind of what it looks like if you're out there hiking around. Now we're almost coming up on time, so I want to quickly kind of talk through how we do exploration. I don't think it'll take too long, but where we know how we know.
Don't worry about the time, Kirsten. We
Okay.
really want to hear what you have to say, so don't feel rushed, I guess is the thing. We'd
Okay.
rather hear it all. Yeah, thank you.
Okay. So I want to talk a little bit through exploration methods, and these are pretty industry standard exploration methods. So if we were to go out looking for anything really, I used to work in planetary exploration actually, and pretty similar methods there too. If you're going to go look for life on Mars or water on the moon, it's pretty similar methods. So I want to start by saying Graphite One was certainly not the first people to be here and not the first people to be looking for stuff or even thinking about the graphite or using the graphite. There's been a long history. Certainly for the last 100 years, there's been various geologists, US agencies studying the graphite, mapping faults, mapping rocks. I came across this quote that back in 1917, a report stated that the graphite had been known for a long time, right? So we don't maybe have much of a written record of that and know the details, but certainly prior to 1917, for previous years, the Tweet family had staked the area and mined graphite from Graphite Creek. There's still really small little adits there. But it mined and shipped it to Seattle and San Francisco. I don't exactly know what that graphite was used for at the time, but I'm sure some industrial purpose, probably something related to what we covered in the first couple slides. And before that, there's a lot of discussion that the local Alaskans used the graphite to lubricate sewing needles or maybe other forms of lubricant or pigments, just as one of the materials that they had access to do human things. You know, humans have lived on this planet as long as we've been humaning, and we've used materials in various ways as long as we've figured out how to use them, really. So I want to start with that. And then certainly in terms of the Graphite One exploration and kind of more, what I'm going to now get into, more traditional exploration methods, started in 2012. And we have not had field programs every summer by any means since then, but about maybe half the summers of various sizes, that slowly collecting data and building up our understanding of the Graphite Creek deposit really in earnest since 2012. So coming back to this picture, this is from 2024. This is our camp out at Graphite Creek at the time. It's a bit smaller now. We pared down the footprint, but one thing I want to have you think about when you look at the mountains, they're certainly beautiful. But I think about how you would figure out what is under the surface. Even trying to figure out what's at surface can be pretty difficult because you have plants and, well, sometimes snow that comes and goes. Sometimes the snow stays in the creeks for a really long time, so it's hard to get to them and see the outcrops that are in there. But certainly a lot of the landscape, and as we've seen really across Alaska, alders are filling in more and more and more of the creeks, and they're covering up outcrops, they're covering up the surface, they're making it harder to see even what's at the surface. And if you want to know what's underneath the surface, I mean, you'd just how good are you at shoveling, It's just not easy to know what's happening in the subsurface. So there's a couple different things we do to try to figure that out. So the first thing we do is we do just walk around the surface and see what we can see, right? When the creeks are melted out, try to walk through the creeks. Usually you get good erosion there, good exposure, and can see beautiful outcrops like this where you can take samples, take measurements, understand which way the rocks are dipping, what the composition of the rocks are, look at the mineralogy, look at the percent of graphite or the percent of any other mineral of interest. And so mapping is one of the first techniques you use walking across the surface. But at some point, you've seen every outcrop that you can find. And usually it's fairly sparse between outcrops. There's a lot of tundra grasses and things between, so it's hard to say what's there. So one of the other techniques that we use a lot are geophysics. And typically you start with aerial geophysics. What that means is that you have a helicopter, that there's various instrumentation you can tie basically behind a helicopter and have them fly. And it sounds pretty wild, but you can go to school for a long time to really understand the math and the physics of all of this, but basically they can fly with these instruments behind them and sense what is in the ground. And a lot of these instruments are passive, so it's not like a seismic hammer or anything that has to like, you know, hit the ground to make a sound and see how that sound wave travels. Like a lot of it's like a passive measurement as it flies over the surface. But you have these helicopters that fly very straight lines, and they try to usually follow as closely to the topography as they can. And they fly a bunch of lines. There was a survey that the Alaska State Survey did up here a couple years back. So if you're in the area, you might have seen some helicopters flying around doing this with funny little wires basically hanging out behind their tail. But the information they can get depends on which instruments they're carrying. In our case, the geophysical surveys that we ran measured specifically conductivity. And if we think about why, we kind of think back to what properties that graphite has. One of its properties is it's highly conductive. And so if we run aerial conductivity surveys, we can start to get a sense for where in the ground we have very conductive minerals. And graphite's not the only highly conductive mineral. There are other ones. So it's not an way to exclusively look for graphite. But what we can say is that graphite is very conductive. And so if we do not see very conductive rocks in the ground, it's unlikely that we have graphite there, right? And especially the kind of graphite that really we'd be looking for from a mining perspective is where we have these big pods of graphite rather than the scattered dispersed graphite. So anywhere that you have these big pods, you should have good electrical connectivity and good conductivity. Strictly speaking, what you actually measure is resistivity, but conductivity and resistivity are two sides of the same coin. They have an inverse relationship. So the more resistance something has, the less conductive it is, right? So if it's less resistive, it's more conductive. And so ultimately we show the data as conductivity because that's the mineral property that we're tracking. So this here, I think it's been shown in pretty widely and shared with the public. And this is data that we collected in an aerial geophysical survey in 2012. And the red colors are highly conductive zones, and the blue colors are low conductivity. So not much conductivity happening in the rocks down here. So if you were to want to use this to look for graphite, you would target the pink red areas and look in those areas first for graphite. And that is something that we have done over time, drilled. So Graphite Creek is right here. And so this zone right here is actually where the main graphite actually comes to surface. That's where you can see it really easily. This is why this has been the focus of the most fieldwork attention so far, because it's a very shallow deposit of graphite right here. We've drilled a couple holes down this line, and it does seem these other zones do correlate to, there's graphite that exists in these as well. But a lot more work would need to be done to understand if every red zone actually has graphite or if it has one of the other high conductivity minerals. What we do know for sure is that this is the zone that has the graphite that we've been focused on. So once we do the mapping that we can and we get some aerial geophysics data, how can we really test what's in the ground? The way we really ultimately test what's in the ground is by drilling into the ground and getting samples. And so what we do is core drilling. This is a picture of a core rig. And this is basically this big mass that comes up. What you do is you take essentially a metal straw and you screw it together and drill it down into the ground. And the straw, so straw is hollow on the inside, and then you have a drill bit that goes around the edge of the straw and drills down. So as you drill down into the earth, you get a tube of rock that comes up into your drill rod. And typically you drill either 5 feet or 10 feet at a time, and then you break off that little tube of rock and bring it back up to surface, and you put it in a box. And that's what you see here in this picture. So these are 3 core boxes pushed together. So here's 1, here's 2, here's 3. And inside here, you see this cylindrical, essentially tube of rock that was pulled out of the ground. So put basically 10 feet of rock in a box, drill down the next 10 feet, put that in a box, drill down, putting that in the box. And that's how we collect core samples. Once we have core samples, they're very precious in that it takes a lot of, it's certainly very expensive to get drill programs set up. It takes a lot of work, it takes a lot of labor, it takes a lot of knowledge and know-how to obtain these materials. And so we always try to keep them as reference materials, but we also do need, and so one thing we do with them first is we log the rocks. And when we log the rocks, we basically go down that tube of rock and give it geologic names. We break it into the units that we see, and we describe those units in great detail. Spend quite a lot of time with geologists poring over these rocks and just, describing them in as great a detail as they can. Ultimately, what we do with that information, so this would be, each of these are examples of drill holes, or these tubes of rock that we have sampled. The diameter here is very exaggerated. Here, this is a cross-sectional view of a 3D model. And here we see, this is basically the surface. We're looking east. This here is just for a reference frame, but it would be, it's the outline of the proposed pit wall. And so the drill holes go to close to the bottom of that pit. So each of these drill holes, all the different colors you see are the different rock units that geologists have logged down each hole. And so this is one of the first things we do. We have a lot of different rock units here with code names. It's not that it's secret, it's more just sort of gets a little boring and in the weeds. And geologists like to argue about what to name everything. But we have these codes that we teach all the geologists when they come on site. And so everyone logs the rocks in the same way, and for the same unit gives the same names. And then ultimately we can get all this data put together and start to see how rock units might connect between the drill holes and start to understand what shape these rock units have in the ground. So the 2 main units here are the green, the dark green, and the lighter green are the 2 main graphite hosting units.
Kirsten, there is a question in the chat. How much is graphite worth? I don't know if that's something you can address.
That is very much outside the scope of this talk, but and the price, from what I understand, the price is constantly changing, but it is not high compared to other. If you think of like how much gold costs per unit and how much gravel, so like a pound of gold versus a pound of gravel, what I can tell you is that graphite is much more similar to the cost of gravel than it is to the cost of gold per pound.
Is it something somebody could look online?
Yeah, I would encourage you to do that.
Okay. I hope that helps, Thomas.
Yeah, so ultimately what we do with this information is we try to understand it in 3 dimensions. So this is a picture, this is a digital elevation. This is basically the terrain right around Graphite Creek and Glacier Canyon Creek over here. And all the little black dots represent drill holes that we have drilled. And the little sticks coming off them are the length, like how deep into the ground that tube of rock went. And you can sort of see here, there's various exploration holes that were drilled, just trying to understand where graphite went. A lot of these holes are from 2012 or 2014, a while back. At some point, we really decided to focus on this zone right here, because this is really where the graphite comes to surface. And so this is where the majority of work has focused in recent years. And it's the area that has been proposed to mine. These holes that you see down here don't go into bedrock at all. Actually, they're drilled to understand the ground conditions, permafrost, water situation in the general area, so that when we do the engineering studies and look at how a mine could be built, we understand the science and the geotech engineering factors that go into planning all of that. So once we have this data in 3D, what we try to do is link the layers together. We have all these holes that are logged. We try to pull all together. We make a geologic model that we can then twirl around in 3D space and understand better what units we have where. And this is a thing that we're constantly refining and constantly working on and trying to understand how these layers sit geometrically in space as best we can. One other thing that happens to the core is that it gets sampled. And so what you do, you take there's that tube of rock, you cut it in half using a core saw, and then one half of it goes through a crusher and pulverizer. So in 1 meter segments, so we do 1 meter sample sizes. And here, these are two of the guys we had working in our sample prep lab in 2024. The crusher's over here. And then we have a pulverizer right here that you can't quite see on the bench. And the guys are working to take this 1 meter of rock, first crush it, then pulverize it, and then I think we got about 200 grams that go into these little sample baggies, little aliquot of this sample, and then the pulverized samples in little baggies go to the chemistry lab. That's a third-party offsite, like a neutral lab that has standards and can officially analyze and document the amount of graphite that's in each of these samples. And so ultimately that's what we do. We send these samples away. We call it for assaying to find out how much graphite is in them. And then we can do things like plot up how much graphite we have in what locations, which units in our drill holes. And once we have that, once we understand how much graphite is where, the data goes to someone we call a resource modeler, and they also work in a 3-dimensional model space like this and calculate. So based on the layers that we think we have in our rock and the assay data that tells us how much graphite we have in different parts of these layers, they compile all that with some quite sophisticated software and calculate how much total graphite exists in these rocks. And so this image here, it's a little hard to see, but the background here is sort of the outline of the proposed pit. The dark gray are several different layers that we think contain graphite. It's hard to see that there's multiple layers here, but really the calculations we've done really just focus in the pit area where we have the high density drilling. You need high density drilling to get good geostatistics to get a better calculation, right? If you don't have much data, your statistics are weaker, and you can't have as high a confidence in knowing how much you have. So where we have the higher density data, that's where we have higher confidence. And that's where we've come up with our mineral resource estimate, which you can see in various publications. And it's a number that I think for most of us is hard to comprehend, but basically, if you think about how much graphite, there's 4.8 million tons of graphite. And this number was arrived on after 155 drill holes that in total added up to about 23,400 meters of drilling, which for people that work on these projects, it kind of gives you a sense of like where the statistics are at on all that. But either way, probably large numbers, but hopefully visually you can kind of get a sense for the number of data points that go into that calculation. And with that, I will stop and be happy to, I guess, answer any questions or, take any questions.
All right. Well, thank you very much, Kirsten. We really appreciate that. And we'll take questions. But first, this is the time we do realize you are you've taken time out of a regular workday and to give us this information, and we really appreciate it. This is the time we ask the Straight Science uh, audience to show some love for the speaker because it's never easy being a public speaker. So, and you did a very good job and told us I've learned lots. I've got some questions, but we'll let others go when they're and everyone's so good now. Emojis. I see that. That's awesome. I don't know if you can see those, Kirsten, but also in the chat. So we very much appreciate learning something new about the Graphite Creek. So with that, any questions? I'll ask the caller first, actually. The caller was on and is still on. That's dedicated calling. If the caller has any questions, feel free to unmute and ask away. You can also text my phone if you need, which is 907-434-1149. And because I know it's tough to be a caller and try to wave attention over to your way. But maybe you have no question. With that, the floor is open.
It's like, I think there is one question
There
in
is.
the
Yep.
chat that I could address.
Yep. How do you ensure homogeneity in the pulverized samples sent for testing?
That is a great question because we definitely want to do that. Basically, as we so we cut the samples in half with a saw, we put that half core into a bag. Ultimately, we dump that bag into a crusher, and the crusher is a very dynamic machine that crushes all of the rock into tiny little pieces, or like a millimeter and smaller. And that crushing process does tend to mix the core quite a bit as a first pass. And then we also then we take that crushed material and we put it into a riffle splitter, which is a sort of cute little contraption. You can basically pour stuff in a couple times, and it has little ramps, little slides that send sample in at least two directions. And we use that to reduce our sample because we don't actually want to send the entire half meter of sample for analysis. So we use the riffle splitter multiple times to reduce our sample size to just the amount that we want to put in the pulverizer to go to the lab. But that riffle splitter process helps mix it quite a lot. And so that is basically the main way that we get things homogenized, by riffle splitting them enough that they get all mixed up.
All right. It's the wiffle splitter. I have a question about the subduction zone going way back in time. So in 2013, we had a Straight Science that was not recorded. We didn't record them back then. We didn't have Zoom, but it was about Pilgrim Hot Springs, and people were trying to make an energy source for that Pilgrim Hot Springs. And I don't think they were able to have much success sort of pinpointing the heat source where that came from. But, for me, you were talking about, I never really thought of us as sort of actively a subduction zone, but that makes sense. And that Pilgrim Hot Springs, are you guys sort of aware of that situation and how it turned out it's the hottest hot spring north of the Aleutians? So it just sort of reminds me that we're in a sort of a very geological, although you wouldn't think it, as many parts of Alaska are seemingly more so, that we have sort of active geologic forces. We actually had a few earthquakes this winter as well, which was odd.
Yeah.
Just this winter. In the last couple of years, we've had them up to I think a 5 right in the Bering Strait.
Yeah.
So
I don't know. There's a lot that I do not know about Pilgrim Hot Springs. In fact, I don't know much about Pilgrim Hot Springs. I think it's pretty neat, and I would love to learn more. It's a pretty neat place, and it sounds like they're also working on understanding their system more. So it'll be really cool to learn more about it as they get more data. One really big part of the geology here that I completely glazed over was that today this dotted line with the little circles on it here is the Kiglualk fault. And it is a very large fault in that it runs quite far to the east. And it drops the ground north of the fault down. So south of the fault here, we have all this rock, and to the north, underneath the Emmerich Basin, we don't actually know how deep you have to go to get to bedrock. And all the stuff that you see on the ground, on the surface here, are sediments that came in and are sitting on top of that bedrock surface because of the down drop block to the north. And no one really knows also even maybe where we call it the hanging wall of the fault, where the hanging wall of the fault is. There's a lot of discussion. I've talked to the USGS geologist. No one's quite sure where it is. So my understanding is that, for one thing, some of the earthquakes could, I don't actually know. I shouldn't say anything about the earthquakes in the area. I have no idea where they're coming from. But there are faults in the region. And my understanding is that Pilgrim Hot Springs, I think some of the warm fluids coming up might be related to this fault because it's sitting out in these sediments. So it's not actually even in the bedrock, but it seems to be related to some current situation that's in these overlying sediments that's north of the Kiglualk fault.
Thank you for that. And I recommend you look, I can talk to you and give you more information about that old study. I mean, it was over a decade ago, hard to imagine. Any other questions? Here's my other question. I know tonight's talk was on graphite, so I hope this isn't kind of a, I'm sure you're a great geologist and I'm sure you'll have this, but I was looking around on the website, the Graphite One Project website before, just to try to learn. I'm not a geologist at all. So just trying to get myself a little familiarized. And I came across the press release that's from last November 25. And it says Graphite One confirms the presence of rare earth elements at its Graphite Creek deposit. And I can put that link in here in the chat. But my question or what kind of rang bells when I was reading through that is, if you live here, you see, not unsurprisingly given our proximity to Chukotka, but you see a lot of military. We have a military history in the region for lots of reasons, and we're seeing it more and more. And we did have but then it was the Department of Defense. It's noticeable to Nome when they are helping fund something. And I think they had done some of that for helping finish up a report or something. And so can you talk at all about those rare earth minerals? Because it seems like there's the graphite, which is a big deal. But then I was like, well, reading that press release, and I'll stick it here. It just seems like maybe there's more that we could probably, you would probably come from there in that.
Potentially, yeah.
Yeah.
So,
And I don't know anything, like I say, about geology. So if you could just sort of educate us on what is rare earth elements and why that's so of interest,
yeah.
Me.
So first of all, rare earth elements are a group of elements in the periodic table, which I could probably show you since I got that table here. They're these guys down here, these blue guys. Those are rare earth elements. The name's a little bit of a misnomer. They're not necessarily super rare. We have them in a number of different rocks. However, they're not usually very concentrated, right? And so trying to find them in places where they're well concentrated and you can easily get them out of the rocks is the challenge. When it comes to Graphite Creek, we'll go back to the pictures here. You recall the rocks that have a lot of graphite in them, these green ones here, also have these garnets that I mentioned. And I started thinking about, okay, I think about, mining from a lot of different perspectives. But one thing is, if you're going to bother to mine something, is it possible to mine more than one thing with this, with the rock you're taking out of the ground? Are we only going to get one thing out of this rock, or can we get multiple things out of this rock, right? To just increase the efficiency. I mean, there's a business case for that. I think there's an environmental case for that. I think there's an ethical case for that. So I started thinking about what other minerals do we have in these rocks, and would there be anything in there of interest? And I have a research background, and I knew that researchers have always used garnets, have specifically used rare earth elements in garnets to understand the metamorphic history of the rocks. And that was just something that people have used to understand other questions and other topics, but I knew that garnets could hold rare earth elements. And so I became curious. Well, I was like, the rocks that we would be mining that have the graphite, those same units have a lot of garnets in them. And are there enough rare earth elements in there to be of interest? Now, the reason the military is interested in rare earths, but really any of us today interact with rare earth elements in ways that we do not realize every day. If you have a computer, if you have a phone, there's little magnets that help drive the electronics, and those are made from rare earth elements, and they're typically made from like we call the heavy rare earth elements, so stuff on the more the right side of the periodic table versus the left side of that little line. But once again, a lot of these rare earths currently are mined and processed in China. Here in the US, we haven't been pursuing them in recent decades, so we don't have supply chains set up to obtain them, to process them, to refine them. But we're realizing that with our electronics, we're more and more dependent on them in the supply chain. And I think all of us in 2020 realized how globalized and interconnected the supply chain is, and how disruptions to the supply chain can really cause havoc. So once people started realizing that most of the stuff comes from China or Russia or other places that, we don't have a say over their policies, we become vulnerable to them shutting that off. So that's why there's folks in the US that are interested in rare earths. The military in particular, I don't know that they necessarily have even more interest in rare earths. Otherwise, they certainly have more interest from a national security perspective in rare earths, but they depend on magnets and computers just like the rest of us. And so they want their magnets and computers to work as well. And so that's kind of the reason they're interested. But at Graphite Creek, I thought it'd be interesting to look and see what other elements we have in our rocks that could be of interest. I did some additional chemical assay work this last year, and one of the things that came out of that was that we do in fact have a higher ratio of heavy rare earths to light rare earths compared to most other rare earth deposits. And our rare earth elements, so they're just the elements, and they're housed in the garnet. What that means is they're not an element that typically makes up garnets, but most minerals have enough void space in their structure that other elements can hop inside and hang out. And that's what happened with these garnets. When this probably, we're looking into this, we have some studies going, but probably typically the way this is envisioned is that during partial melting, fluids carrying these rare earth elements can come by the garnets. The garnets are growing. They can get basically trapped inside the rooms of the garnet structure. And so if you dissolve the garnets, you can get rare earth elements out of them. And so that's the connection. Does that make sense?
Yep. Then I appreciate that. There is a question in the chat from Cara. She asks, I'm not sure which map this is, but stand by. Why is there a little red blob? Oh, that's it, maybe. Why is there a little red blob north of the Kig fault line? And I actually had one too. What's the orange box? But look on a different map you have, but let's get this one done for. And how are you holding up? We're talking geology and you've been going strong. It's almost 8 o'clock. So
yeah, I'm getting pretty tired here, but we can answer these last few questions.
Okay.
Great question. I did just say that there's just sediments north and not bedrock, but this red blob suggests that there's bedrock north. I don't exactly know what's happening here. I have not been here. What I suspect there is a little blob that seems to be sticking up and out. And so whether it's like a down drop block that just slid off the north end and is sitting out in the basin, or whether it is poking through the sediments, I'm not quite sure. So that's a good observation that is in fact there. I can't fully answer your question, I think, because I haven't actually been there myself. I'm not quite sure what's going on there. And
All right.
then
The you had a map kind of looking down, and you had
yeah, I'm trying to
those
think. I think
little
that's this direction.
blue,
I
lot of
think
blue.
this
No,
orange box.
there you go. I
Oh
thought, well,
yeah,
look at that.
this is just a mistake on my slide. I meant to
Okay.
I meant to have this little orange box right here to show what we're zoomed
Okay.
into, but
Sorry
I
about that. Sorry.
didn't get it moved over.
Sorry. All right. Well, we're kind of, I think we've run the speaker pretty hard. Matthew in the chat says, is there potential for rare earth minerals to be mined at Graphite Creek? If so, how would the mine plan change if rare earth metals would be mined along with the graphite?
Yeah, good question. So kind of the reason we're even looking at this at all is that the garnets will get mined anyways as we mine the graphite because they're in the same units. So from that perspective, not much changes. Most likely. We're at a very, very early stage understanding the rare earth minerals. And so we do not know yet enough about their distribution to know honestly if it would change the mine plan much, but probably it'd be like more like tweaking the plan versus dramatic changes because they're already in the rocks that are planning to get mined. What would change is like we'd want to figure out how to separate them out, and there's various known techniques for how to do that. And so things would probably change a little bit in like maybe how we stockpile materials or how we basically we would try to then separate out the garnets instead of just sending them all to what we call the tailings or the rock that gets left behind. So things would change there, but at this point, it's early enough stage that like I have absolutely no specifics that I could give you on that, which really comes down to the data that we'll be collecting in the future to understand a lot of that.
All right. I'm going to stop your share so we can
Hello?
see you because you're, oh, hello. Is it
Yeah,
the
I
call?
finally figured out. Yep, it seemed to
Hey.
work.
Okay. Well, I
Yeah,
know it's tough being a caller. Go ahead.
I want to know how deep the samples are.
How deep the
Yeah.
samples are.
So the drill hole, so everything's in meters. I'll try to convert to feet. Typically our drill holes only go down about 250 meters. They don't go super deep. I mean, that's all relative, I guess. But so I think maybe 600 feet into the
And of
subsurface.
course,
Something
they're
like that.
filled back in again.
And the question is, are they filled back in again?
Oh, so what happens is that we don't want to put, so you don't put you don't put like rock back down the hole because the core gets stored in boxes. But what you do is you plug the top of the hole. So there's various ways that you close off. You basically, plug the top of the hole typically with cement so that nothing can get in or out once you've drilled the hole and taken the core.
How many?
How many drill holes?
How many? Yeah.
Do you mean, so the caller, do you mean that they've done for testing? Because I think what they're thinking about is when they're mining, they're gonna, it looks like make a pit. They're just gonna take it all, not just do these little drill holes are for testing. And I just did my Google, 250 meters is 820 feet. So I think this is all part of the test, is my understanding, but maybe the speaker can educate me. Sounds like it's testing, and then they put a cover on it. Yeah. If I got that right, Kirsten?
Yeah, so the drill holes now are to understand, to get data about what's in the ground right now. So this, well, I guess you can't see on the phone, but we have, we've drilled about 155 drill holes that are each various different lengths, but different lengths, all adding up to about, yeah. So each hole is between, say, 50 and 800 feet. And
How wide is the hole?
yeah, that's a good question. The diameter, it's about the size of a baseball in diameter.
Like that.
That's the size of the core that comes out. And so that hole, it's plugged at surface so that nothing can get in or out at surface.
Does that help you, caller?
Yep.
Okay. Thank you for your question. I'm glad you could unmute. I tried to do things on my phone.
Yeah.
I'm not very good. All right. Any other questions for our speaker, Kirsten Fristad? You have gone past the 8 o'clock mark, so we really appreciate that. And with that, we'll let everybody go on with their evening. Kirsten, if you could stay for just one sec. Next week's Strait Science will be on Wednesday, June 3rd, and it's going to be an update on the bird flu situation for Alaska's wildlife. We're going to have the U.S. Geological Survey, Andy Ramey, and St. Jude's Children's Research Hospital who are going to be here in Nome. That Strait Science will be available via Zoom and also in person at the UAF Northwest Campus Education Center, the big building behind the Science Lab, north of the Science Lab. With that, thank you all for coming and have a good night, everybody. We'll see you Wednesday.